Atmospheric water harvesting. Capturing water from air is nothing new. It is believed, for instance, that the early Greeks who established Theodosia, currently known as Phaeodosia, in the 6th century BC utilized bowl-shaped stone condensers to capture water in the air to fulfill their daily water needs. Our circumstances, however, are vastly different. Though over 70% of Earth's surface is covered with water, only a tiny percentage of freshwater available today on the surface of rivers, wetlands, lakes, and swamps is considered potable for humans. Improper management of water reservoirs, contamination of drinking water sources, high industrial and domestic water demand, human conflicts, increasing construction, industrial, and agricultural development, and climate change have been continuously contributing to the decrease in drinking water over the last few decades. According to the United Nations Children's Emergency Fund, UNICEF, approximately 4 billion people worldwide encounter severe water scarcity for at least 1 month each year. Over half of the world's population could be residing in countries where continuous water supply will be inadequate as early as 2025. Water scarcity has become a global challenge and is expected to be exacerbated over the next few years. As a consequence, there is considerable interest worldwide in sustainable solutions that provide safe drinking water for everyone. Several technologies, including wastewater recycling, seawater desalination, and rainwater harvesting, have been investigated for their capacity to alleviate water scarcity. However, each of these techniques possesses its own practical issues. Atmospheric water harvesting, AWH, technology has recently emerged as a promising alternative that decentralizes water access using the overlooked water available in the Earth's atmosphere. The potential of AWH could be tremendous. Earth's water cycle plays a crucial role in the biosphere, and the Earth's atmosphere holds approximately 10% of freshwater found in all lakes and rivers, equivalent to 12,900 billion tons of freshwater, irrespective of the geographical area and hydrologic conditions. The AWH technology is a process of extracting and collecting freshwater from surrounding, ambient, air as water vapor or droplets. This technology is based on a bulk phenomenon where vapor or liquid molecules present in the atmosphere diffuse into solid materials or sorbents, altering the structure and volume of sorbents via physical interaction or chemical reaction with the sorbent. Modern AWH technologies can be divided into 3 main classes based on their energy utilization. 1. Passive water harvesting systems that operate without additional energy input. 2. Active water harvesting systems that work with additional energy input such as electricity. 3. And solar-driven hygroscopic water harvesting systems. Generally, passive water harvesting systems are easy to construct, but their water extraction capacity is extremely small. The active water harvesting systems, including systems involving membrane separation and thermoelectric cooling, are sophisticated, larger, and require relatively high amounts of electrical energy. However, their water extraction processes produce a relatively large amount of water. The solar-driven hygroscopic, absorbs water from air, water harvesting systems are considered the most promising due to their simple, easy installation, low cost, and environmental friendliness. These solar-driven AWH generators are based on the adsorption-desorption process, and use hygroscopic sorbents, including metal-organic frameworks, MOFs, hybrid crystalline porous materials, polymeric and porous adsorbents and hydrogels. Among the many sorbents, hydrogels have attracted significant attention as atmospheric water harvesters owing to their superior hydrophilicity, readily absorbing or dissolving in water, tunable surface characteristics, mechanical and thermal properties, low cost, easy functionalization, relative abundance of raw materials, renewability, and eco-friendliness. Hydrogels are three-dimensional, 3D, cross-linked networks of a hydrophilic polymer that can absorb and retain water without deforming its structure. Generally, a hydrogel consists of approximately 10% water by total weight, or volume. Hydrogels can be categorized based on the source, natural or synthetic, polymeric configuration, crystalline, semicrystalline or amorphous, polymeric composition, homopolymeric, copolymeric or multipolymeric, network cross-linking, chemical and physical, or network electrical charge, neutral, anionic, cationic and zwitterionic, having both positive and negative charge. Zwitterionic hydrogels are a novel class of hydrogels that possess positively charged cationic and negatively charged anionic functional groups along with their polymer chain. In contrast to other hydrogels, zwitterionic hydrogels contain hygroscopic salts such as lithium chloride, LiCl, and calcium chloride, CaCl2, in their matrix, causing the coalescence of small water droplets into larger droplets. The hygroscopic salt coordinated with the polymer chain could potentially extract moisture via the anti-polyelectrolyte effect, or how its zwitterion's polymer chains shrink in water but expand in salt solutions. First, the hygroscopic salts present in the matrix extract the water from the atmosphere and facilitate the in situ, on-site, liquefaction. Subsequently, the water is adsorbed to the hydrogel. The presence of hygroscopic salts also improves the swelling property of the zwitterionic hydrogels, leading to higher water storage. For instance, a zwitterionic hydrogel can expand 100 to 1,000-fold in the presence of desalinated water. The presence of positively and negatively charged functional groups on the zwitterionic hydrogels helps the salt become more stable and prevents leaching from the matrix and deterioration of its structure. Therefore, zwitterionic hydrogels are considered a promising strategy for AWH, as demonstrated by a recent study by Lay and co-workers, in which they achieved an AWH capacity of 0.62 g of water vapor sorption per gram of their zwitterionic hydrogel, over 120 minutes at 30% relative humidity, with a daily freshwater production of 5.87 L per kilogram of hydrogel. Another study by Aliad and co-workers also devised a solar-driven zwitterionic hydrogel with carbon nanotubes, CNT, as the photothermal component, which achieved an AWH capacity of 1.30 g of water vapor sorption per gram of their zwitterionic hydrogel, at 25 degrees Celsius and 60% relative humidity. Figure 2 shows the schematic representation of the water adsorption mechanism of zwitterionic hydrogel loaded with LiCl. As shown in Figure 2, the presence of LiCl enhances the water adsorption and swelling of the zwitterionic hydrogel. Unlike many other hydrogels, zwitterionic hydrogels are suited for all-weather moisture harvesting, and can thus provide freshwater for arid and landlocked regions. In addition to its use in AWH technology, zwitterionic hydrogels have major implications for production of electricity. The zwitterionic hydrogels-based energy generator is driven by the mechanical movement that is based on the antipoly-electrolyte effect. Hydrogels placed in a cylindrical piston can be continually moved upwards and downwards during the water adsorption and desorption of water by transforming the antipoly-electrolyte effect into a mechanical force. In conclusion, hydrogel-based AWH technologies, including zwitterionic hydrogels, show great promise in extracting water from humid air, a large reservoir of water that is accessible in many areas of the world. Moreover, zwitterionic hydrogels can be used as all-weather water harvesters. Although hydrogel-based AWH technologies are at the developmental stages and showing significant promise, there is still much work to be performed to establish zwitterionic hydrogels as energy-efficient, sustainable, industrially scalable, and cost-effective AWHs. With widespread attention received, due to their high water harvesting capacities, polyswitterionic hydrogels could play an immense role in supplying water for arid regions, potable water production, and emergency post-disaster situations in the future.